Every second, the Sun converts 600 million tons of hydrogen into helium, releasing energy equivalent to 90 billion megatons of TNT, a sustained explosion that has continued for 4.6 billion years and will persist for another 5 billion. This process involves no combustion, requires no oxygen, produces no smoke, and operates through physics fundamentally different from every fire humanity has ever witnessed on Earth. The misconception that the Sun burns like a campfire persists despite centuries of scientific understanding to the contrary. We use the word burn colloquially. We say the Sun burns bright, that it burns hydrogen. But this linguistic convenience obscures a profound truth. The Sun doesn't burn at all in any conventional sense. No chemical reactions occur in the solar core. No molecules break apart and recombine. No electrons transfer between atoms to release stored chemical energy. Instead, the Sun operates through nuclear fusion, a process where atomic nuclei, the dense cores of atoms containing protons and neutrons, slam together with such violence that they overcome electromagnetic repulsion and merge, converting mass directly into energy according to Einstein's famous equation, E=mc2. A single kilogram of matter, converted entirely to energy, yields 90 trillion joules, equivalent to the explosion of 21 megatons of TNT. The Sun performs this mass-to-energy conversion at rates exceeding 4 million tons per second. This distinction between combustion and fusion isn't merely academic semantics. It represents one of the most profound discoveries in the history of physics, that matter and energy are interchangeable, that the periodic table emerges from fusion processes in stellar cores, that the universe operates on principles invisible in everyday experience. Understanding why the Sun doesn't burn but instead fuses reveals the quantum mechanical underpinnings of reality and the nuclear physics governing stellar evolution. For most of human history, the Sun's energy source remained mysterious. Ancient civilizations attributed solar power to gods or supernatural forces, Ra carrying the Sun across the sky, Helios driving his chariot, various mythologies explaining daylight through divine action. Early scientific investigations made little progress because the governing physics lay beyond available theories and observations. By the 19th century, scientists recognized the problem. Chemical combustion couldn't sustain the Sun's luminosity for more than a few thousand years. Coal or wood fires would exhaust available fuel almost immediately on astronomical timescales. Gravitational contraction proposed by Lord Kelvin and Hermann von Helmholtz suggested the Sun might shine from slowly shrinking and converting gravitational potential energy to heat. This mechanism could power the Sun for roughly 20 million years, a dramatic improvement but still far too short given geological evidence for ancient Earth. The breakthrough came in the early 20th century with quantum mechanics and nuclear physics. Arthur Eddington proposed in 1920 that subatomic energy sources might power stars, suggesting that somehow hydrogen might transform into helium and release energy. Hans Bethe in 1939 worked out the detailed nuclear reactions, the proton-proton chain and CNO cycle that convert hydrogen to helium in stellar cores. These mechanisms could sustain the Sun for billions of years, matching geological and astrophysical constraints. The core temperature required for fusion, approximately 15 million Kelvin, creates conditions so extreme that matter exists in a state called plasma, where electrons separate from nuclei and atoms lose all molecular structure. At these temperatures, there are no molecules, no chemical bonds, no possibility of combustion as we understand it. The physics governing solar energy production operates at nuclear scales, mediated by quantum mechanics and the strong nuclear force, rather than electromagnetic interactions between electrons. The Sun's luminosity, 3.8 x 1026 watts, represents the aggregate result of countless fusion reactions occurring throughout a core volume, roughly 100,000 kilometers in radius. Each individual reaction releases approximately 26.7 MeV of energy, a tiny amount by macroscopic standards. but approximately 9x 1037 fusion reactions per second sum to the Sun's total power output, demonstrating how quantum-scale processes aggregate to create observable cosmic phenomena. The energy released in the core doesn't immediately escape. Photons produced by fusion scatter through the dense solar plasma, taking a random walk that requires 100,000 to 200,000 years to traverse from core to surface. A distance light could travel in 2.3 seconds through vacuum. This delayed energy transport explains why the Sun's surface temperature, approximately 5800 Kelvin, is vastly cooler than the core despite being the same object. Understanding solar fusion has implications extending far beyond explaining how our star works. The same physics governs all stars, from red dwarfs barely massive enough to sustain fusion to massive blue giants fusing elements far heavier than helium. The fusion processes in stellar cores create every element heavier than hydrogen and helium, the carbon in our bodies, the oxygen we breathe, the iron in our blood, all forged in stellar furnaces and scattered through space by supernova explosions. Tonight, we're going to explore exactly how nuclear fusion works, why it requires no oxygen, how quantum mechanics allows fusion despite electromagnetic repulsion, and what this reveals about the fundamental physics governing our universe. We'll trace energy from the solar core through radiation and convection zones to the surface, examine the spectroscopy proving the Sun contains no fire, and understand why this process represents one of nature's most elegant mechanisms for converting mass to energy. Before we begin exploring nuclear physics and stellar structure, if you're fascinated by how the Sun generates energy through processes fundamentally different from anything we experience on Earth, subscribe and hit the thumbs up button. And here's a question. If you could witness one astrophysical process in person from a safe distance, what would you choose? Comment below, I'll pin the most creative answer. The distinction between combustion and fusion, between chemical and nuclear energy, between molecular bonds and strong nuclear force, these aren't just technical details for specialists. They represent fundamental insights into how the universe operates, how energy flows through cosmic structures, and why stars shine. The Sun doesn't burn, it fuses, and understanding that difference opens windows into physics at its most fundamental. Now let's begin by understanding combustion, what fire actually is, why it requires oxygen, and why this process cannot possibly power the Sun. The nature of fire. Fire represents a chemical process, specifically rapid oxidation, where fuel molecules react with oxygen, breaking chemical bonds in fuel and forming new bonds in combustion products, while releasing the difference in bond energies as heat and light. Understanding fire's true nature reveals immediately why it cannot possibly power the Sun and why our everyday experience with flames provides misleading intuition about stellar energy. Combustion requires three components: fuel, oxygen, and sufficient activation energy to initiate the reaction. When wood burns, complex organic molecules, cellulose, lignin, various hydrocarbons, decompose from heat and react with atmospheric oxygen. The carbon atoms in these molecules form new bonds with oxygen atoms, creating carbon dioxide. Hydrogen atoms bond with oxygen, producing water vapor. The energy released comes from the difference between the chemical bond energies in the reactants and products. Chemical bonds hold atoms together through electromagnetic interactions between electrons. When carbon burns, forming carbon dioxide, the reaction releases approximately 4 electron volts per carbon atom. The energy difference between carbon-oxygen bonds in CO2 and the original carbon-carbon and carbon-hydrogen bonds in the fuel, plus the oxygen-oxygen bonds in O2. This energy appears as kinetic energy of the product molecules, heat, and as photons, light, and infrared radiation. The temperature of typical fires reveals their energy scale. Wood fires reach temperatures around 600–900 Celsius. Propane torches achieve roughly 1900 Celsius. Even the hottest chemical flames, oxygen-acetylene torches used in welding, barely exceed 3000 Celsius. These temperatures reflect the energy scales of chemical bonds which involve electron interactions and energies measured in electron volts. The visible light from flames comes from incandescent soot particles and excited molecules emitting photons as they return to lower energy states. The characteristic yellow-orange color of wood fires results primarily from blackbody radiation from hot carbon particles, while the blue regions of flames indicate hotter temperatures and different chemical species emitting at shorter wavelengths. Combustion is fundamentally limited by the availability of chemical energy stored in molecular bonds. The most energy-dense chemical reactions, hydrogen combusting with oxygen to form water, release approximately 3 electron volts per hydrogen molecule. This represents an upper limit for chemical energy density because hydrogen-oxygen bonds are among the strongest chemical bonds nature provides. Calculating how long chemical combustion could power the Sun reveals the impossibility immediately. The Sun's mass is approximately 2A1030 kilograms. If the entire Sun consisted of hydrogen and oxygen in ideal proportions for combustion, and if somehow all of it could react simultaneously, the total chemical energy available would be roughly 1044 joules, an enormous amount by terrestrial standards but utterly insufficient for stellar timescales. The Sun's luminosity, 3.8 T-26 watts, would exhaust this hypothetical chemical fuel in approximately 1044 joules, 3.8 × 1026 watts, yielding roughly 8,000 years. Even if we generously assume perfect efficiency and ideal fuel composition, chemical combustion could power the Sun for at most tens of thousands of years. Geological evidence proves Earth is billions of years old, and the Sun must have shined throughout Earth's history to maintain temperatures suitable for liquid water and life. Furthermore, combustion requires continuous oxygen supply. Fires on Earth draw oxygen from the atmosphere. Approximately 21% of Earth's air by volume consists of O2 molecules. In space, no such reservoir exists. The Sun sits in vacuum with essentially no molecular oxygen in its vicinity. Even if chemical combustion could somehow initiate, it would immediately extinguish from lack of oxidizer. The Sun's spectrum, the distribution of light across different wavelengths, provides direct evidence against combustion. Flames produce characteristic emission lines from excited molecules and atoms. Sodium produces yellow lines, copper produces green, calcium produces orange-red. These emission features result from electrons in excited atoms dropping to lower energy levels and releasing photons at specific wavelengths determined by quantum mechanics. The solar spectrum shows absorption lines, not emission lines characteristic of flames. These absorption features occur when cooler gas in the Sun's outer layers absorbs specific wavelengths from the continuous spectrum produced by deeper, hotter layers. The pattern of absorption lines reveals the Sun's composition, primarily hydrogen and helium with traces of heavier elements, but shows no evidence for the molecular species and combustion products that would appear in flame spectra. Spectroscopic analysis definitively rules out oxygen-based combustion in the Sun. If the Sun were burning in any conventional sense, we would detect strong oxygen emission or absorption features, along with molecular bands from water vapor, carbon dioxide, and other combustion products. Instead, the spectrum shows atomic hydrogen and helium dominating, with oxygen present only in trace amounts as individual atoms rather than molecular O2. The temperature profile also excludes combustion. The Sun's core reaches 15 million Kelvin, far beyond temperatures where molecules can exist. At temperatures exceeding a few thousand Kelvin, molecular bonds break apart from thermal energy, dissociating molecules into constituent atoms. Above roughly 10,000 Kelvin, atoms themselves become ionized as electrons gain sufficient energy to escape atomic nuclei. The solar core exists at temperatures where matter is fully ionized plasma, no molecules, no chemical bonds, no possibility of chemistry as we understand it. The energy density difference between chemical and nuclear processes illustrates the fundamental distinction. Chemical reactions involve rearranging electrons and typically release energies, of a few electron volts per atom. Nuclear reactions involve rearranging protons and neutrons within atomic nuclei and release energies measured in millions of electron volts, MeV rather than EV. This million-fold difference in energy scale means that nuclear processes can sustain stellar luminosity for billions of years, while chemical processes exhaust themselves in millennia. Understanding fire's true nature, electromagnetic interactions between electron clouds, energy measured in electron volts, temperatures reaching a few thousand degrees at most, establishes the baseline for appreciating the fundamentally different physics governing solar energy. The Sun operates in a regime where chemical bonds cannot exist, where electrons separate from nuclei, where temperatures and densities create conditions utterly alien to terrestrial experience. The historical confusion about solar energy persisted precisely because fire represented the only energy source humanity understood for millennia. We saw the sun producing light and heat, analogous to flames, and naturally assumed similar mechanisms. This intuitive leap, while understandable, missed the profound truth that nature operates on multiple energy scales with fundamentally different physics at each level. Antoine Lavoisier's 18th century work establishing the oxygen theory of combustion represented a major advance, explaining fire as chemical combination rather than release of a hypothetical substance called phlogiston. But even this correct understanding of terrestrial combustion couldn't explain stellar energy. The physics governing stars operates at scales Lavoisier's chemistry couldn't address. The realization that combustion cannot power the sun came gradually through the 19th century as scientists calculated energy budgets and recognized the impossibility. This negative result, determining what the sun is not, proved as important as eventually determining what it is. Science advances not just through discoveries, but through rigorous elimination of possibilities, constraining theories until only truth remains consistent with observations. Fire teaches us about chemical energy, molecular bonds, and electron interactions. These lessons remain valid and important for understanding terrestrial phenomena, chemistry, and everyday experience. But they also reveal their own limitations. Chemical energy scales cannot explain stellar phenomena. The sun requires different physics, operating at different energy scales, governed by forces that don't appear in everyday chemistry. The quest to understand solar energy thus became a quest to understand physics beyond the electromagnetic interactions governing chemistry. It required discovering nuclear structure, quantum mechanics, the strong nuclear force, and mass energy equivalence. The sun's light demanded we expand our understanding of nature's fundamental laws. Plasma state. The sun exists in a state of matter fundamentally different from the solids, liquids, and gases we experience on Earth. At temperatures exceeding 10,000 Kelvin, matter transforms into plasma, the fourth state of matter, where electrons separate from atomic nuclei and electromagnetic interactions create collective behaviors impossible in ordinary gases. Understanding plasma physics is essential for understanding how the sun operates and why conditions in stellar interiors permit nuclear fusion. In ordinary gases like Earth's atmosphere, atoms and molecules remain intact. Electrons orbit nuclei, chemical bonds form and break, but the fundamental atomic structure persists. Increasing temperature adds kinetic energy, atoms and molecules move faster, collide more violently, but remain recognizable as distinct particles with electrons bound to nuclei. At sufficiently high temperatures, thermal energy exceeds the binding energy holding electrons in atomic orbits. Electrons gain ionized kinetic energy to escape from nuclei entirely, creating a soup of positively charged ions and negatively charged free electrons. This ionized gas constitutes plasma, a state where electrostatic interactions between charged particles dominate the physics rather than the neutral particle collisions governing ordinary gases. The sun's core temperature, approximately 15 million Kelvin, ensures complete ionization. No neutral atoms exist at these temperatures. Hydrogen atoms dissociate into free protons and electrons. Helium atoms lose both electrons, becoming bare alpha particles, nuclei consisting of 2 protons and 2 neutrons. Any heavier elements present exist as fully stripped ions with all electrons removed. This ionization fundamentally changes how matter behaves. In neutral gases, particles interact primarily through short-range forces during collisions. In plasmas, charged particles interact through long-range electromagnetic forces, the Coulomb force, which extends over large distances and affects many particles simultaneously. This creates collective behavior where the plasma responds as a whole to electromagnetic fields rather than as individual particles. Plasma oscillations exemplify this collective behavior. If you displace electrons slightly from ions in a plasma, the electrostatic attraction pulls them back, but their momentum carries them past equilibrium, creating oscillations at the plasma frequency. These oscillations depend on electron density and charge, occurring at characteristic frequencies determined by plasma properties rather than individual particle motions. The Debye length quantifies another plasma characteristic, the distance over which electric fields are screened by mobile charges. In the Sun's core, the Debye length is approximately 10 to 11 meters, far smaller than the average distance between particles. This short screening length means that individual charged particles interact primarily with their immediate neighbors. Long-range forces are screened by the collective response of intervening charges. Plasma beta, the ratio of thermal pressure to magnetic pressure, determines whether thermal or magnetic forces dominate plasma dynamics. In the Sun's core, plasma beta vastly exceeds unity, meaning thermal pressure dominates. Magnetic fields, though present, exert minimal influence on core dynamics. Higher in the solar atmosphere, in the chromosphere and corona, beta drops below unity and magnetic forces become dominant. These forces drive phenomena like solar flares and coronal mass ejections. The extreme density of the solar core, approximately 150,000 kilograms per cubic meter, roughly 150 times the density of liquid water, creates conditions where quantum effects become important despite the high temperature. The average distance between particles is roughly 10 meters, smaller than typical atomic radii in ordinary matter. Particles are packed so densely that quantum mechanics constrains their behavior through the Pauli exclusion principle and degeneracy pressure. Degeneracy pressure, arising from quantum mechanics, demand that fermions like electrons occupy distinct quantum states, provides additional pressure beyond thermal pressure. In the Sun's core, thermal pressure dominates, but degeneracy pressure contributes measurably. In more compact objects like white dwarfs, where density vastly exceeds even the solar core, degeneracy pressure becomes the primary support against gravitational collapse. The opacity of the solar plasma, how easily photons can travel through it, determines energy transport. At core temperatures and densities, photons scatter frequently from free electrons and ions through processes like Thomson scattering and free absorption. The mean free path for photons, the average distance traveled between interactions, is approximately 1 centimeter in the core. Energy transport through this opaque plasma occurs primarily through radiative diffusion rather than direct photon propagation. Radiative diffusion works like heat conduction in solids, but mediated by photons. Energy released in nuclear reactions creates photons that scatter in random directions. They gradually work their way outward through countless scattering events. This random walk process is extraordinarily slow. A photon's path from core to surface, if traced, would measure countless light years despite the Sun's 700,000 kilometer radius. The transit time reaches 100,000 to 200,000 years. The temperature gradient in the radiative zone, the region extending from about 0.25 to 0.7 solar radii, where radiative diffusion dominates, is determined by energy flux, opacity, and the requirement that energy flow outward at a rate balancing core energy production. The temperature drops from roughly 7 million Kelvin at the radiative zone's base to about 2 million Kelvin at its top. It decreases gradually as photons diffuse outward. Above the radiative zone, in the convection zone, energy transport changes mechanism. When the temperature gradient becomes steep enough that radiation can't transport energy efficiently, plasma becomes convectively unstable. Hot plasma rises, cool plasma sinks, creating turbulent convection cells that transport energy far more efficiently than radiative diffusion. This convection creates the granulation pattern visible on the sun's surface. Bright cells appear where hot plasma rises. Dark boundaries appear where cooler plasma descends. Plasma instabilities can disrupt stable configurations, driving dynamic phenomena throughout the solar atmosphere. The Rayleigh-Taylor instability occurs when dense plasma sits above less dense plasma. It creates characteristic filamentary structures. The Kelvin-Helmholtz instability develops at velocity shear boundaries. It produces rolled vortex structures. These instabilities play roles in solar phenomena from convection cell dynamics to prominence eruptions. Magnetic fields in the convection zone get tangled and amplified through dynamo action. The combination of plasma rotation and convection generates and maintains magnetic fields. These fields emerge through the photosphere to create sunspots, active regions, and complex coronal magnetic structures driving space weather. The solar dynamo remains incompletely understood. It represents an active research area in solar physics. The solar wind, a continuous outflow of plasma from the sun, demonstrates how plasma can escape stellar gravity. Thermal pressure and wave heating in the corona accelerate plasma to velocities exceeding the escape velocity. This creates a supersonic flow that streams through the solar system at hundreds of kilometers per second. This wind carries magnetic fields. It creates the heliosphere, a bubble of solar plasma and magnetic field extending beyond the outer planets. Understanding plasma physics is essential for fusion energy research on Earth. Attempts to recreate stellar fusion conditions in laboratories, tokamaks, stellarators, inertial confinement fusion, must contain and control plasmas at temperatures exceeding 100 million Kelvin. These temperatures are hotter than the solar core to compensate for lower densities. The challenges of plasma confinement, instability control, and sustained fusion represent major technological hurdles toward practical fusion power. The plasma state also dominates much of the visible universe. Stars are plasma. The interstellar medium contains ionized gas. Accretion disks around black holes are plasma. Galaxy clusters contain diffuse hot plasma. The early universe, shortly after the Big Bang, existed entirely as plasma before cooling enough for neutral atoms to form. Understanding plasma physics provides insights into phenomena across cosmic scales. The solar plasma's properties, temperature, density, composition, ionization state, can be measured through spectroscopy and helioseismology. Absorption and emission lines reveal temperatures and densities at various depths. Sound waves propagating through the solar interior create surface oscillations. Helioseismologists analyze these oscillations to map internal structure. This works much like seismologists use earthquakes to map Earth's interior. These techniques confirm theoretical models of solar structure and plasma properties. The transition from ordinary gas to plasma occurs gradually as temperature increases. Different elements ionize at different temperatures depending on their electron binding energies. Hydrogen ionizes around 13.6 eV, corresponding to approximately 100,000 Kelvin. Helium requires higher temperatures to remove both electrons. The solar chromosphere, a thin layer above the visible surface, represents a transition region where ionization gradually increases. The state changes from mostly neutral to mostly ionized as temperature rises from 6,000 Kelvin to 1,000,000 Kelvin over a few thousand kilometers. Atomic structure. Understanding solar fusion requires understanding atomic structure, the organization of protons, neutrons, and electrons into the elements filling the periodic table. Nuclear physics operates at scales 100,000 times smaller than atomic scales, where the strong nuclear force, rather than electromagnetic force, dominates, and where quantum mechanics governs behavior in ways that seem impossible from everyday experience. The atom's nuclear model, established through experiments by Ernest Rutherford and colleagues in the early 20th century, revealed that nearly all atomic mass concentrates in a tiny central nucleus, while electrons orbit in a surrounding cloud. The nucleus measures roughly 10 to 15 meters across, a femtometer, also called a Fermi. Typical atomic radii measure roughly 10 meters, 100,000 times larger. The atom is mostly empty space, with the nucleus occupying approximately 1/trillionth of the atom's volume. Protons and neutrons compose atomic nuclei. Protons carry positive electric charge exactly equal in magnitude to the electron's negative charge, with mass approximately 1,336 times the electron mass. Neutrons carry no charge and have mass slightly greater than protons, about 0.1% heavier. Both protons and neutrons belong to a class of particles called baryons, which are themselves composed of quarks bound by the strong force. The number of protons in a nucleus defines the element. Hydrogen contains 1 proton, helium contains 2, carbon contains 6, oxygen contains 8, iron contains 26. This atomic number determines the element's chemical properties because it determines how many electrons surround the nucleus in a neutral atom, and electron configuration governs chemical behavior. Isotopes of a given element contain the same number of protons but different numbers of neutrons. Hydrogen has 3 isotopes: protium with no neutrons, deuterium with 1 neutron, and tritium with 2 neutrons. These isotopes have nearly identical chemical properties because chemistry depends on electron interactions, but vastly different nuclear properties because nuclear stability depends on the proton-neutron ratio. Nuclear binding energy, the energy required to disassemble a nucleus into separate protons and neutrons, reveals why fusion releases energy. When protons and neutrons bind into nuclei, the strong nuclear force creates a system with lower mass than the separated constituents. This mass deficit, called the mass defect, converts to binding energy via EEXEMC2. Iron 56 has the highest binding energy per nucleon, meaning it's the most tightly bound nucleus. Fusion of lighter elements releases energy up to iron, while fission of heavier elements releases energy beyond iron. The strong nuclear force, one of nature's 4 fundamental forces, binds protons and neutrons into nuclei. This force operates only at extremely short ranges, roughly 1 femtometer, but at those distances it vastly exceeds electromagnetic repulsion between protons. The strong force is charge independent, meaning it attracts protons to protons, neutrons to neutrons, and protons to neutrons with approximately equal strength. The electromagnetic force, another fundamental force, creates repulsion between protons because they carry like electric charges. This Coulomb repulsion extends over long ranges and works to tear nuclei apart. Stable nuclei exist only when the short-range, strong attraction overcomes long-range electromagnetic repulsion. Small nuclei like helium-4 achieve this easily. Larger nuclei require increasing proportions of neutrons to provide additional strong attraction without adding electromagnetic repulsion. Uranium-238, one of the heaviest naturally occurring nuclei, contains 92 protons and 146 neutrons, nearly 60% neutrons. This neutron excess is necessary to provide sufficient strong force attraction to barely overcome the electromagnetic repulsion from 92 protons. Beyond uranium, nuclei become so large that no neutron addition can stabilize them against electromagnetic disruption, hence the lack of stable superheavy elements in nature. The Coulomb barrier represents the electromagnetic potential energy barrier preventing protons from approaching close enough for the strong force to bind them. 2 protons approaching each other experience repulsion that increases as they get closer, creating an energy hill that must be climbed before they can reach strong force distances where attraction takes over. This barrier's height for hydrogen fusion is roughly 500 keV, far higher than typical thermal energies in the solar core. Quantum tunneling, a phenomenon with no classical analogy, allows particles to pass through energy barriers they classically couldn't surmount. In quantum mechanics, particles have wave-like properties, and these wave functions extend into classically forbidden regions. There's a small but non-zero probability that a particle on one side of a barrier appears on the other side without having possessed sufficient energy to climb over classically. This tunneling probability depends exponentially on barrier width and height. Wider and higher barriers exponentially suppress tunneling. For proton fusion at solar core temperatures, tunneling probability is extremely low. Roughly 1 collision in 10^26 results in fusion. But with approximately 1057 protons in the solar core undergoing countless collisions per second, even this tiny probability produces roughly 9 × 10^37 fusion reactions per second, sufficient to maintain solar luminosity. The Maxwell-Boltzmann distribution describes particle speeds in thermal plasma. At any given temperature, particles have a range of velocities, with most moving at speeds near the thermal average, but some moving much faster or slower. The high-energy tail of this distribution, particles moving faster than average, contributes disproportionately to fusion because tunneling probability increases exponentially with particle energy. The Gamow peak represents the sweet spot where two competing factors maximize fusion rate. Increasing particle energy increases tunneling probability, but decreases the number of particles with that energy due to the Maxwell-Boltzmann distribution's exponential tail. The Gamow peak occurs at the energy where the product of these factors, number of particles times tunneling probability, reaches maximum, typically at energies somewhat above the thermal average. For solar core conditions, temperature around 15 million Kelvin, corresponding to average thermal energy roughly 1.3 keV, the Gamow peak for proton-proton fusion occurs around 10 keV. Particles with this energy contribute most to fusion, despite being relatively rare, because their higher energy greatly increases tunneling probability compared to typical thermal particles. Electron screening reduces the effective Coulomb barrier in dense plasma. In the solar core, free electrons swarm around protons, partially screening their positive charge and reducing the electromagnetic repulsion experienced by approaching protons. This screening effect, though modest, measurably enhances fusion rates compared to isolated protons in vacuum, roughly 10 to 20% increase in reaction rate at solar densities. Nuclear cross-sections quantify fusion probability. Defined as an effective area presented by a nucleus to incoming particles, cross-sections for proton-proton fusion at Gamow peak energies are approximately 10 to the 23 square centimeters, many orders of magnitude smaller than atomic cross-sections. This tiny cross-section reflects the extreme difficulty of bringing protons close enough to fuse despite thermal energies far below the Coulomb barrier height. Measuring nuclear cross-sections in laboratories provides the data needed to calculate stellar fusion rates. Experiments accelerate particles to controlled energies and measure fusion probabilities, mapping cross-sections as functions of energy. These measurements, extrapolated to stellar energies, feed into stellar models predicting energy generation rates, lifetimes, and evolution. The solar neutrino problem, which persisted from the 1960s through the 1990s, arose from measurements detecting only about 1/3 the predicted neutrino flux from solar fusion. This discrepancy suggested either that solar models were wrong or that neutrino physics was incomplete. The resolution came through discovering neutrino oscillation. Neutrinos change flavor as they travel from Sun to Earth, and early experiments detected only one flavor. Modern experiments observing all neutrino flavors confirm the total flux matches predictions. validating solar models. Nuclear physics determines not just whether fusion occurs, but also the specific pathways and products. The proton-proton chain, the dominant fusion pathway in the Sun, proceeds through multiple steps, each with its own cross-section and branching ratio. Understanding these pathways required decades of nuclear physics research, measuring reaction rates and decay properties of unstable nuclei produced as intermediates. The carbon-nitrogen-oxygen cycle, an alternative fusion pathway catalyzed by carbon, nitrogen, and oxygen, dominates in hotter, more massive stars but contributes only about 1.7% of solar energy production. The CNO cycle's temperature sensitivity means it becomes increasingly important in stars somewhat more massive than the Sun, eventually dominating energy production in stars above roughly 1.3 solar masses. Nuclear fusion. Nuclear fusion, the process powering the Sun, occurs when atomic nuclei overcome electromagnetic repulsion through quantum tunneling and merge, creating heavier nuclei and releasing energy from the mass difference between reactants and products. Understanding fusion requires examining the specific reactions converting hydrogen to helium in the solar core, the energy released at each step, and why this process can sustain stellar luminosity for billions of years. The proton-proton chain begins when two protons collide with sufficient energy and quantum tunnel through the Coulomb barrier to reach distances where the strong nuclear force binds them. Most collisions fail. Even at solar core conditions, only approximately one collision in 1026 results in fusion. This extraordinarily low probability means individual protons in the solar core undergo fusion on average once every 9 billion years. The Sun sustains its luminosity through the sheer number of protons available. Roughly 1057 protons in the core means billions of fusion events per second, despite the low per-particle probability. The first step produces deuterium, heavy hydrogen, with one proton and one neutron, but two protons cannot bind stably. The electromagnetic repulsion would tear them apart. Instead, during the brief moment when two protons approach strong force distances through tunneling, one proton must undergo beta plus decay, converting to a neutron, positron, and neutrino. This transformation requires the weak nuclear force, which operates even more slowly than tunneling probability suggests, making the first step the slowest and rate-limiting stage of the entire chain. The reaction is P plus P, 2H plus E plus plus Ni, where P represents a proton, 2H represents deuterium, E plus represents a positron, and Ne represents an electron neutrino. The positron quickly annihilates with an ambient electron, converting their combined mass to gamma-ray photons with total energy 1.022 MeV. The neutrino escapes the Sun at nearly the speed of light, carrying away roughly 0.26 MeV on average. These neutrinos provide our only direct window into the solar core because they interact so weakly with matter that they pass through the Sun essentially unimpeded. The deuterium produced in step 1 doesn't persist long. Deuterium fuses with protons far more readily than protons fuse with each other. The cross-section is much larger. Within roughly 1 second of formation, the deuterium nucleus encounters a proton and fuses to form helium-3, 2H plus P, 3He plus Gry. This reaction releases a gamma-ray photon carrying 5.49 MeV of energy. The helium-3 nucleus, containing 2 protons and 1 neutron, faces multiple possible fates, creating 3 branches of the proton-proton chain. The dominant branch, PPI, occurs when 2 helium-3 nuclei collide and fuse, 3He plus 3He, 4He plus 2P. This reaction produces a stable helium-4 nucleus, an alpha particle, and releases 2 protons back into the plasma to participate in future fusions. The energy released is 12.86 MeV. Summing the complete PPI chain, 4 protons convert to 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and gamma rays. The net energy release accounting for neutrino losses is approximately 26.7 MeV. This energy appears as kinetic energy of the product particles and photons, which thermalize through collisions and contribute to the thermal energy, maintaining core temperature and pressure. The mass energy accounting reveals fusion's power. 4 hydrogen nuclei have combined mass 4.032 atomic mass units. 1 helium-4 nucleus has mass 4.03 atomic mass units. The mass deficit, 0.029 AMU, or about 0.7% of the initial mass, converts to energy via EIMC2. This 0.7% conversion efficiency vastly exceeds chemical reactions efficiency, typically 10-8%, explaining why fusion can power stars for billions of years while combustion exhausts itself in thousands. The pp2 branch occurs when helium-3 fuses with existing helium-4 rather than another helium-3, 3He plus, 4He, 7b plus. The resulting beryllium-7 captures an electron, 7b plus E, 7 Li plus Ni, producing lithium-7 and a neutrino. The lithium then fuses with a proton, 7 Li plus P, 24 He, producing 2 helium-4 nuclei. This branch contributes roughly 14% of solar energy production and produces higher energy neutrinos detectable in solar neutrino experiments. The pp3 branch proceeds when beryllium-7 captures a proton instead of an electron, 7b plus P, 8b plus Krieg, producing boron-8. The boron undergoes beta plus decay, 8b plus E plus Ni, producing beryllium-8, which immediately splits into 2 helium-4 nuclei. This branch contributes only 0.02% of solar energy, but produces the highest energy neutrinos, up to 15 MeV, making them easier to detect despite their rarity. The temperature sensitivity of fusion reactions determines stellar structure and evolution. The proton-proton chain's rate increases approximately with the 4th power of temperature. Doubling temperature increases fusion rate by a factor of 16. This strong temperature dependence creates a natural thermostat. If core temperature increases, fusion rate spikes, increasing energy production, expanding the core, reducing density and temperature until equilibrium restores. If temperature drops, fusion slows, reducing pressure, allowing contraction that raises temperature again. The CNO cycle, carbon-nitrogen-oxygen cycle, provides an alternative fusion pathway converting hydrogen to helium using carbon as a catalyst. The cycle begins with carbon-12 capturing a proton to form nitrogen-13, which beta decays to carbon-13, which captures another proton to form nitrogen-14. Nitrogen-14 captures a proton forming oxygen-15, which beta decays to nitrogen-15, which captures a proton and immediately splits into carbon-12 and helium-4. The carbon-12 is regenerated and available to catalyze another cycle. The CNO cycle's temperature dependence is even stronger than the proton-proton chain, roughly the 17th power of temperature. This extreme sensitivity means CNO fusion barely operates at solar core temperatures, but dominates in stars with core temperatures above roughly 18 million Kelvin. More massive stars have hotter cores due to higher gravitational compression, making CNO their primary energy source. The CNO cycle's high temperature sensitivity also creates convective cores in massive stars. Energy generation concentrates near the center, where temperatures peak, creating steep temperature gradients that drive convection. Measuring fusion reactions in laboratories faces challenges because stellar energies, a few keV, lie far below what accelerators typically achieve, and cross-sections at these energies are vanishingly small. Experiments accelerate particles to the lowest possible energies, tens of keV, and measure cross-sections, then extrapolate to stellar energies using theoretical models. These measurements require sophisticated underground detectors shielded from cosmic rays to reduce background noise. The Lunar Experiment, Laboratory for Underground Nuclear Astrophysics, operates in the Gran Sasso Underground Laboratory in Italy using a low-energy accelerator in a low background environment to measure fusion cross-sections at energies approaching the gamma peak for solar conditions. These measurements have refined our understanding of specific reaction rates, improving solar models, and resolving discrepancies between theoretical predictions and observations. Helium accumulation in the solar core gradually changes composition over the Sun's lifetime. When the Sun formed 4.6 billion years ago, the core was roughly 71% hydrogen and 27% helium by mass. Today, after 4.6 billion years of fusion converting hydrogen to helium, the core composition is approximately 34% hydrogen and 64% helium. This helium enrichment increases mean molecular weight, requiring higher temperatures to maintain pressure support against gravity. The Sun's luminosity has increased roughly 30% since formation due to this composition change. Higher mean molecular weight requires higher core temperature to maintain hydrostatic equilibrium, and higher temperature drives faster fusion, increasing luminosity. This slow brightening has implications for Earth's climate history. The faint young sun paradox asks how Earth maintained liquid water in the past, despite receiving less solar radiation. Greenhouse gases likely played a stronger role in Earth's early atmosphere. Eventually, approximately 5 billion years from now, the solar core will exhaust its hydrogen fuel. Fusion will cease in the core, removing the pressure support that balances gravity. The core will contract, heating from gravitational potential energy conversion until a shell surrounding the now helium core reaches temperatures sufficient for hydrogen fusion. This shell burning will cause the Sun to expand into a red giant, engulfing the inner planets and dramatically altering the solar system. Much later, after sufficient contraction raises core temperature to approximately 100 million Kelvin, helium fusion will ignite through the triple alpha process. 4He plus 4He, 8Be, followed by 8B plus 4He, 12C. Beryllium-8 is highly unstable, decaying in 10 to 16 seconds, but in the high-density helium core, enough beryllium exists transiently that some captures a third helium nucleus before decaying, building carbon. Further helium capture converts carbon to oxygen, 12C plus 4He, 16O. The Sun will end its life as a carbon-oxygen white dwarf after shedding its outer envelope as a planetary nebula. Energy transport, energy produced by fusion in the solar core, doesn't immediately reach the surface and radiate into space. Instead, it embarks on a journey lasting 100,000 to 200,000 years, traveling through the radiative zone via photon diffusion, then through the convection zone via bulk plasma motion, before finally escaping from the photosphere. Understanding this energy transport reveals why the Sun's surface temperature is so much cooler than the core and how stellar structure self-regulates. Photons created in fusion reactions begin with energies in the gamma-ray range, millions of electron volts. These high-energy photons immediately collide with surrounding plasma, free electrons, protons, helium nuclei. Each collision can scatter the photon in a random direction or be absorbed and re-emitted at different energy. The photon's path becomes a three-dimensional random walk, taking countless steps in random directions before making net progress outward. The opacity of the solar plasma, its effectiveness at absorbing and scattering radiation, determines how far photons travel between interactions. In the solar core, the mean free path for photons is approximately 1 centimeter. After traveling 1 centimeter on average, a photon scatters or gets absorbed and re-emitted, starting a new random step in a new random direction. This random walk process is extraordinarily inefficient for net outward progress. A photon might travel 1 centimeter, then scatter backward, then sideways, gradually working outward, but with most steps contributing little to net radial distance. The time required for a photon to diffuse from core to surface can be estimated from the radiative diffusion equation. T R2 chi c tel, where R is solar radius, c is light speed, and L is mean free path. Plugging in numbers, R 7x 105 kilometers, c 3x 105 kilometers per second, L 0 to 1 meters. The diffusion time is roughly 7x108 meters to 3x108 meters second x 0.01 meters, 1013 seconds, 170,000 years. This represents the characteristic timescale for energy produced in the core to reach the surface. Energy we see as sunlight today was produced before modern humans evolved. During this journey, photons undergo countless scatterings and absorptions. Each absorption-emission cycle can shift the photon's energy. High-energy gamma rays gradually degrade to X-rays, then ultraviolet visible light, and infrared as energy redistributes among many lower-energy photons. By the time energy reaches the photosphere, the spectrum has thermalized. It follows the Planck blackbody distribution corresponding to the photosphere's 5 in 800 Kelvin temperature, rather than retaining memory of the high-energy gamma rays produced in fusion. The temperature gradient in the radiative zone is determined by energy flux, opacity, and the requirement that radiative diffusion transport energy at the rate produced by core fusion. The temperature drops from roughly 7 million Kelvin at the base of the radiative zone to about 2 million Kelvin at the top, spanning a distance from roughly 0.25 to 0.7 solar radii. This gradient is gentle enough that radiative diffusion remains stable. Steep gradients would drive convection, as occurs in the outer layers. Opacity depends on plasma composition, temperature, and density. Free electrons scatter photons via Thomson scattering, a process that doesn't depend strongly on photon energy for energies below electron rest mass energy. Bound free absorption occurs when photons ionize atoms, removing electrons from bound states. Free absorption happens when free electrons in the electric field of ions absorb photons and gain kinetic energy. Each process contributes to total opacity, which varies throughout the Sun as conditions change. Heavy elements, anything heavier than hydrogen and helium, contribute disproportionately to opacity despite their low abundance. Atoms with many electrons provide many bound states for photon absorption, and partially ionized atoms are especially effective absorbers. The solar metallicity, roughly 2% heavy elements by mass, significantly affects opacity and therefore energy transport efficiency and stellar structure. The Rosseland mean opacity, a particular averaging of opacity over photon energies weighted by the temperature gradient, determines radiative diffusion efficiency. This quantity appears in the fundamental equation relating temperature gradient to energy flux in radiative equilibrium. Stellar evolution models require accurate opacity calculations which come from atomic physics computations and laboratory measurements compiling databases of absorption cross-sections for millions of atomic transitions. At approximately 0.7 solar radii from the center, the temperature gradient becomes steep enough that radiative diffusion cannot transport energy efficiently. The Schwarzschild criterion for convective stability is violated. A parcel of plasma displaced upward would find itself hotter and less dense than surroundings, causing it to continue rising rather than sink back. This marks the base of the convection zone, where energy transport mechanism changes from radiation to convection. Convection transports energy through bulk mass motion. Hot plasma near the convection zone base rises, expanding and cooling adiabatically as it ascends. When it reaches the photosphere, it has cooled to roughly 5800 Kelvin and radiates energy into space. The cooled plasma, now denser than its surroundings, sinks back down, completing a convection cell. This process transports energy far more efficiently than radiative diffusion. Convection timescales are days to weeks rather than millennia. The solar granulation pattern, visible on the Sun's surface with appropriate telescopes, reveals individual convection cells. Each granule represents a rising column of hot plasma, appearing bright against the darker, intergranular lanes where cooler plasma descends. Typical granules measure 1,000 to 2,000 kilometers across and last 10 to 20 minutes before breaking up and being replaced by new granules. The Sun's surface churns continuously with this convective overturn. Supergranulation, a larger-scale convective pattern spanning 30,000 kilometers, also appears on the solar surface. These cells last days and transport magnetic fields, creating the network pattern visible in magnetograms. Giant cells spanning the entire convection zone may also exist, though they're difficult to observe directly and remain somewhat uncertain in models. The mixing caused by convection homogenizes the convection zone composition. Any material reaching the convection zone gets thoroughly mixed throughout the zone within roughly 1 million years, a short time scale compared to the Sun's age. This explains why the solar surface composition matches the composition of material that has never undergone fusion. The radiative zone below prevents mixing with the core, so surface observations reveal the Sun's initial composition modified only by processes occurring in the convection zone or outer layers. Lithium depletion provides evidence for convective mixing depth. Lithium burns at temperatures around 2.5 million Kelvin through the reaction 7 Li plus P, 24 He. The Sun's surface shows lithium abundance roughly 140 times lower than primordial meteoritic values. This depletion results from convection dredging surface material down to depths where temperature exceeds 2.5 million Kelvin, destroying lithium before returning the material to the surface. The observed depletion constrains convection zone depth and models of solar interior structure. Heliosismology, studying solar oscillations, provides direct measurements of solar interior structure, testing theoretical models. The Sun rings like a bell with millions of oscillation modes, each characterized by specific frequencies determined by sound speed profiles throughout the interior. Observing these frequencies reveals interior temperature, density, and composition profiles with precision rivaling or exceeding theoretical models. The sound speed in the solar interior ranges from roughly 500 kilometers per second near the photosphere to about 500 kilometers per second in the core. Accurate sound speed profiles derived from helioseismic inversions match theoretical predictions to better than 0.2% in the radiative zone, confirming our understanding of energy transport, equation of state, and opacity. Small discrepancies near the convection zone base reveal inadequacies in modeling convective overshooting, the penetration of convective motion into the radiative zone. The time delay between fusion energy production and surface radiation creates a thermal inertia, stabilizing the Sun. If fusion suddenly stopped, the Sun wouldn't immediately go dark. Stored thermal energy would continue radiating for tens of thousands of years as energy already in the radiative diffusion pipeline slowly leaked out. Conversely, sudden changes in fusion rate take millennia to affect surface luminosity, buffering rapid fluctuations and creating long-term stability. This energy transport timescale explains why the Sun's luminosity responds slowly to composition changes from fusion. Over billions of years, helium accumulation increases mean molecular weight, requiring higher core temperature to maintain pressure, driving higher fusion rates and luminosity. But these changes occur over millions to billions of years, far longer than energy transport timescales, allowing quasi-equilibrium between fusion, transport, and radiation. The Sun's composition, temperature, and lack of combustion can be determined definitively through spectroscopy, the analysis of light as a function of wavelength. The solar spectrum reveals that the Sun consists primarily of hydrogen and helium with trace amounts of heavier elements, contains no molecular oxygen or combustion products, and emits radiation characteristic of a hot, dense plasma rather than chemical flames. Understanding spectroscopy provides the observational foundation, proving the Sun doesn't burn. Isaac Newton's discovery that white light separates into a rainbow of colors when passed through a prism established the foundation for spectroscopy. In 1814, Joseph von Fraunhofer observed that the solar spectrum, when examined at high resolution, contained hundreds of dark lines, specific wavelengths where light was missing from the otherwise continuous rainbow. These Fraunhofer lines represented absorption of specific wavelengths by cooler gas in the Sun's outer layers. Each element produces a unique pattern of spectral lines determined by quantum mechanics. Electrons in atoms occupy discrete energy levels, and transitions between levels require photons with energy exactly matching the energy difference. Hydrogen's Balmer series transitions to the second energy level, produces absorption lines at wavelengths 656 nm H-alpha, 486 nm H-beta, 434 nm H-gamma, and shorter wavelengths following a precise mathematical formula discovered by Johann Balmer in 1885. The Lyman series transitions to hydrogen's ground state, falls in the ultraviolet, and can only be observed from space because Earth's atmosphere absorbs UV radiation. The Paschen, Brackett, and Pfund series transitions to higher levels, fall in the infrared. Together, these series create hydrogen's complete spectral fingerprint, allowing definitive identification even when mixed with emissions from other elements. Helium was discovered through spectroscopy before being found on Earth. During the solar eclipse of 1868, Pierre Janssen and Norman Lockyer independently observed a bright yellow emission line at 587.6 nm that didn't match any known element. Lockyer proposed it came from a new element he named helium after the Greek word for sun, helios. Nearly 3 decades later, in 1895, William Ramsay isolated helium gas on Earth by heating cleveite ore, finally confirming that this solar element existed terrestrially. The strength of spectral lines, how much light gets absorbed, depends on the abundance of the element, the temperature and density of the gas, and the quantum mechanical properties of the particular transition. The Boltzmann equation describes how atoms distribute among energy levels at a given temperature, determining what fraction of atoms can participate in particular transitions. The Saha equation determines ionization state as a function of temperature and density, establishing how many atoms have electrons available for transitions. Measuring the sun's composition requires modeling how line strength depends on these factors. Simply measuring that hydrogen lines are strong doesn't immediately tell you hydrogen's abundance. You must account for temperature, density, ionization state, and atomic physics. Sophisticated radiative transfer codes model how photons propagate through solar plasma, calculating expected line profiles for assumed compositions and comparing with observations to infer actual abundances. The solar photospheric composition determined through spectroscopy shows approximately 73% hydrogen, 25% helium, and 2% heavier elements by mass. This composition matches predictions from Big Bang nucleosynthesis. The universe should have formed with roughly 75% hydrogen and 25% helium, with stars then enriching the interstellar medium with heavy elements produced through fusion and supernovae. The absence of molecular oxygen spectral features proves definitively that the Sun contains no O2. Molecular oxygen produces characteristic absorption bands in the visible and near-infrared from electronic transitions and vibration rotation transitions. These features appear prominently in Earth's atmospheric spectrum. Oxygen's A band at 762 nm and B band at 687 nm are strong atmospheric features. They're completely absent in the solar spectrum, confirming no molecular oxygen exists in the Sun. Similarly, the absence of water vapor bands, carbon dioxide absorption features, and other molecular signatures expected from combustion products proves chemical burning doesn't occur. High-resolution solar spectroscopy reveals absorption lines from atomic species, neutral and ionized atoms, but no molecular features except for a few molecules like carbon monoxide and titanium oxide that can survive in the cooler regions of sunspot umbra and the solar photosphere. The continuous spectrum underlying the absorption lines follows Planck's blackbody law for a source at approximately 5800 Kelvin. Blackbody radiation represents thermal emission from matter in thermodynamic equilibrium, where emission and absorption balance, and the spectrum depends only on temperature. The solar photosphere approximates a black body because the plasma is dense enough and optically thick enough that photons thermalize before escaping. Wien's displacement law, Lmax, sectional 2.9x10, 3 atomic K, T, relates peak wavelength to temperature. For T, Prandtl 5800K, peak wavelength falls around 500 nanometers in the green portion of the spectrum. This explains why the Sun appears yellowish-white. It emits across the visible spectrum with peak emission in green, but our eyes and atmosphere integrate this to perceive yellowish color. The Stefan-Boltzmann law, L-4PR2ST4, relates luminosity to radius and temperature, where S is the Stefan-Boltzmann constant. Measuring the Sun's angular size from Earth and its distance determines its radius. Measuring total radiation received at Earth and accounting for distance determines luminosity. These measurements confirm temperature estimates from the spectral shape, providing consistency checks between different observational methods. Line broadening mechanisms provide additional information about solar conditions. Natural broadening arises from Heisenberg's uncertainty principle. Energy levels have finite width due to their finite lifetime. Thermal broadening results from Doppler shifts from atoms moving at different velocities in the hot plasma. Hotter temperatures produce wider lines. Pressure broadening occurs when collisions perturb atomic energy levels, creating broader absorption features. Denser plasma shows stronger pressure broadening. Measuring line profiles, the detailed shape of absorption features, reveals temperature, density, pressure, and velocity information at different heights in the solar atmosphere. The photosphere, chromosphere, and corona produce lines with different characteristics, allowing three-dimensional mapping of solar atmospheric structure through spectroscopy alone. Zeeman splitting, the splitting of spectral lines in magnetic fields, allows measurement of magnetic field strength and geometry. George Ellery Hale discovered this effect in sunspots in 1908, providing the first evidence that sunspots are regions of intense magnetic fields. Modern magnetographs exploit Zeeman splitting to map magnetic fields across the solar surface, revealing active regions, the global dipole field, and the complex topology driving solar activity. Solar spectroscopy from space, free from atmospheric absorption, accesses ultraviolet and X-ray wavelengths, revealing hotter plasma in the chromosphere and corona. Extreme ultraviolet emission from highly ionized iron, Fe9 through Fe15, indicates temperatures from 1 to 3 million Kelvin. X-ray emission from even more highly ionized species reveals coronal temperatures exceeding 10 million Kelvin in active regions. The UV and X-ray spectrum's intensity and spectral distribution prove that solar atmospheric heating mechanisms operate beyond simple radiative equilibrium. The temperature increases from 5800 kK at the photosphere to millions of Kelvin in the corona despite moving farther from the energy source, an inverted temperature gradient requiring energy input. Magnetic reconnection, wave dissipation, and other processes evidently heat the outer atmosphere, though the exact mechanisms remain actively researched. Neutrino detection provides the only direct spectroscopy of the solar core. Neutrinos produced in fusion escape the Sun within seconds, carrying information about core conditions. The Homestake experiment, beginning in 1970, first detected solar neutrinos using a tank of cleaning fluid deep underground. Neutrino interactions converted chlorine-37 to argon-37, which was chemically extracted and counted. The solar neutrino problem, detecting only 1/3 the expected neutrinos, drove decades of research culminating in the discovery of neutrino oscillation. The Sudbury Neutrino Observatory, using heavy water to detect all neutrino flavors, showed that the total neutrino flux matches theoretical predictions when all flavors are counted. This confirmed both solar fusion models and new physics regarding neutrino properties. Modern neutrino detectors like Borexino measure the complete neutrino spectrum from different fusion branches. pp, pep, 7be, 8b neutrinos, comparing fluxes, tests, fusion models and constraints, core temperature and composition. Agreement between observations and predictions to within a few percent confirms our understanding of solar energy generation with precision impossible through electromagnetic observations alone. Spectroscopy thus provides overwhelming evidence that the Sun operates through nuclear fusion rather than combustion. Hydrogen and helium dominate composition, no oxygen molecules or combustion products exist, temperatures far exceed anything compatible with chemistry, and neutrino fluxes confirm nuclear reactions at rates matching luminosity. The Sun's spectrum reveals its secrets to those who know how to read the language of light. Historical understanding. Humanity's path to understanding solar energy generation wound through centuries of speculation, false starts, and gradual accumulation of physical knowledge. The Sun's power source remained one of nature's deepest mysteries until the 20th century brought quantum mechanics, nuclear physics, and the observational tools needed to test theories against reality. This historical journey reveals how scientific understanding progresses through creative hypothesis, rigorous testing, and willingness to overturn cherished ideas when evidence demands. Ancient civilizations recognized the Sun's importance for agriculture, seasons, and life itself, but lacked frameworks for understanding its physical nature. Greek philosophers speculated that the Sun might be a ball of fire, with Anaxagoras proposing around 450 BCE that it was a mass of blazing metal larger than the Peloponnese, a remarkably accurate assessment of size if not composition. Aristotle placed the Sun in the celestial realm, fundamentally different from earthly matter and governed by different laws. The Copernican revolution displaced Earth from the cosmic center, but didn't immediately illuminate the Sun's nature. Galileo's telescopic observations of sunspots revealed surface features and rotation, but provided no insight into energy generation. Isaac Newton's laws explained planetary orbits but didn't address stellar physics. The question remained, what keeps the Sun shining? By the 19th century, with thermodynamics established and energy conservation understood, scientists could formulate the question quantitatively. What energy source can sustain solar luminosity for geological timescales? Measurements of solar radiation reaching Earth, combined with Earth-Sun distance, established that the Sun radiates approximately 3.8 1026 watts continuously, an enormous power output demanding explanation. Julius Robert von Meyer proposed in the 1840s that meteoritic infall might power the Sun, gravitational potential energy converting to heat as meteors crashed into the solar surface. Calculations quickly showed this mechanism required impractically large meteorite masses and would measurably alter Earth's orbit through gravitational effects that weren't observed. The hypothesis failed quantitative tests. Hermann von Helmholtz and Lord Kelvin proposed gravitational contraction in the mid-1800s, the Sun slowly shrinking and converting gravitational potential energy to heat. This Kelvin-Helmholtz mechanism provided a plausible energy source operating over longer timescales than combustion. Calculations suggested contraction could power the Sun for approximately 20 million years, a vast improvement over chemical energy. However, geological evidence increasingly pointed to Earth ages exceeding billions of years. Charles Lyell's principles of uniformitarianism in geology required vast timescales for gradual processes to shape Earth's surface. Darwin's theory of evolution demanded hundreds of millions to billions of years for natural selection to produce observed biological diversity. The conflict between Kelvin's solar age and biological evidence created a crisis in late 19th century science. The discovery of radioactivity by Henri Becquerel in 1896 and subsequent work by Marie and Pierre Curie revealed that atomic nuclei contain enormous energy. Ernest Rutherford's 1904 suggestion that radioactivity might provide Earth's internal heat and extend geological timescales pointed towards solutions but the specific mechanism for solar energy remained unclear. Arthur Eddington's 1920 presidential address to the British Association for the Advancement of Science proposed that subatomic energy might power stars, specifically suggesting that hydrogen might somehow convert to helium. Eddington noted that 4 hydrogen atoms have slightly greater mass than 1 helium atom, and if this mass deficit converted to energy via E=mc2, the energy released would be enormous, sufficient to power the Sun for billions of years. Eddington's proposal faced immediate criticism. The temperatures in stellar cores, estimated at millions of degrees, seemed insufficient to overcome electromagnetic repulsion between protons. Classical physics predicted that protons would need temperatures of billions of degrees to collide with sufficient energy to penetrate the Coulomb barrier. Stars simply weren't hot enough for fusion under classical physics. The resolution came through quantum mechanics, specifically quantum tunneling. George Gamow, working with quantum theory in the late 1920s, recognized that particles have wave-like properties, allowing them to pass through potential barriers with some probability, even when they lack sufficient classical energy to overcome the barrier. Robert Atkinson and Fritz Houtemans applied this insight to stellar fusion in 1929, showing that quantum tunneling could allow fusion at temperatures of tens of millions of degrees rather than billions. Hans Bether's 1939 papers, Energy Production in Stars, detailed the proton-proton chain and carbon-nitrogen-oxygen cycle, the specific nuclear reactions converting hydrogen to helium in stellar cores. Bethe calculated reaction rates, energy releases, and temperature sensitivities, showing that these mechanisms quantitatively explained stellar luminosities and lifetimes. This work earned Bethe the 1967 Nobel Prize in Physics for contributions to the theory of nuclear reactions, especially discoveries concerning the energy production in stars. Fred Hoyle's work in the 1940s and 1950s extended stellar nucleosynthesis beyond hydrogen and helium, showing that fusion in massive stars and supernovae could produce all elements up to iron through the periodic table. Burbage, Fowler, and Hoyle's landmark 1957 paper, often called B2FH, comprehensively described how stellar fusion creates the elements, explaining the cosmic abundances observed in spectroscopy. The solar neutrino problem emerged when Raymond Davis's homestake experiment, beginning observations in 1970, detected only about 1/3 the neutrinos predicted by solar models. This discrepancy persisted for decades and generated 2 possible explanations. Either solar models were fundamentally wrong, or neutrino physics was incomplete. Most physicists suspected neutrino physics was the issue because solar models were constrained by many independent observations: luminosity, age, composition, helioseismology, all pointing to consistent core conditions. The solution came through discovering neutrino oscillation, the phenomenon where neutrinos change flavor as they propagate. The Sudbury Neutrino Observatory's results in 2001-2002 definitively showed that solar neutrinos produced as electron neutrinos oscillate to muon and tau neutrinos during transit from Sun to Earth. Early experiments detected only electron neutrinos, missing 2/3 of the total flux. ESNO's heavy water detector could measure all neutrino flavors, confirming the total flux matched solar model predictions. This resolution validated both solar physics and revealed new particle physics. Neutrinos have mass and mix among flavors, properties not accommodated in the standard model of particle physics as originally formulated. The solar neutrino problem's solution thus advanced knowledge in 2 fields simultaneously, demonstrating how apparently discrepant observations can drive fundamental discoveries. Helioseismology, developing from the 1970s onward, provided increasingly precise tests of solar models. The Global Oscillation Network Group, Solar and Heliospheric Observatory, and other projects mapped millions of solar oscillation modes. Inverting these frequency measurements revealed interior sound speed, density, and composition profiles matching theoretical predictions to better than 1% precision. This agreement confirmed that models correctly describe solar structure from core to surface. Modern solar physics represents a triumph of interdisciplinary science, synthesizing quantum mechanics, nuclear physics, atomic physics, thermodynamics, fluid dynamics, magneto-hydrodynamics, and observational astronomy into a coherent picture explaining how the sun works. From Eddington's speculative proposal to Bethy's detailed mechanisms to neutrino observations confirming core conditions, the century-long effort to understand solar energy generation demonstrates how science progresses through creative theorizing constrained by rigorous observation. The historical journey also illustrates how wrong ideas get discarded when evidence accumulates against them. Meteoritic infall seemed plausible initially, but failed quantitative tests. Gravitational contraction explained some observations but conflicted with geological timescales. Each wrong idea contributed to understanding by constraining possibilities and highlighting what needed explaining. Contemporary research continues refining our understanding. Precise measurements of solar abundances reveal discrepancies between photospheric and meteoritic compositions that weren't previously appreciated, creating the solar abundance problem, where updated photospheric measurements conflict slightly with helioseismic constraints. Resolving this requires either better opacity calculations, revised abundance determinations, or modifications to solar models, active research areas today. The study of other stars illuminates solar physics through comparison. Observing stars at different masses, ages, and compositions tests whether our theoretical understanding generalizes beyond the Sun. Binary stars provide mass measurements. Variable stars provide distance calibrations. Stellar populations at different metallicities test how composition affects structure. The Sun, as our nearest and best-studied star, anchors stellar astrophysics while also representing a single example of a vastly diverse population. Understanding how the Sun generates energy through fusion provides the foundation for stellar astrophysics, the study of how all stars form, evolve, and die. The same physics governing solar fusion operates in stars throughout the universe, but variations in mass, composition, and age create diverse stellar populations with different fusion pathways, lifetimes, and evolutionary endpoints. Examining stellar physics reveals the Sun's place in the broader context of cosmic structure and evolution. Stellar mass determines almost everything about a star's properties and fate. The fundamental reason is that more massive stars have stronger gravitational fields requiring higher core pressures to achieve hydrostatic equilibrium, and higher pressure requires higher temperature from the ideal gas law. Higher core temperature drives faster fusion through the strong temperature dependence of nuclear reaction rates, increasing luminosity. The mass-luminosity relation for main sequence stars follows approximately LM35 for stars near solar mass, meaning a star twice the Sun's mass has roughly 11 times solar luminosity. More massive stars show even steeper scaling, LM2 to M3 for the most massive stars. This relationship emerges directly from the physics of hydrostatic equilibrium, energy transport, and fusion temperature sensitivity. Stellar lifetimes depend inversely on mass because, while fuel supply scales linearly with mass, luminosity scales much faster than linearly. A 2-solar mass star has twice the fuel, but 11 times the luminosity, exhausting hydrogen in roughly 1/5 the time, about 2 billion years compared to the Sun's 10 billion year main sequence lifetime. Massive stars live fast and die young, with 10 solar mass stars lasting only 30 million years and 50 solar mass stars exhausting core hydrogen in just 3 million years. The fusion pathway dominating energy production depends on core temperature. The proton-proton chain operates efficiently at solar core temperatures around 15 million Kelvin. The CNO cycle requires higher temperatures to overcome larger Coulomb barriers for carbon, nitrogen, and oxygen nuclei, becoming competitive around 17 million Kelvin and dominating above 18 million Kelvin. Stars more massive than roughly 1.3 solar masses have cores hot enough for CNO dominance. The CNO cycle's high temperature sensitivity, rate proportional to temperature to the 17th power, creates convective cores in massive stars. Energy generation concentrates sharply near the center, where temperature peaks, creating steep temperature gradients that exceed the radiative equilibrium threshold and drive convection. These convective cores mix material, bringing fresh hydrogen to the center and homogenizing composition throughout the convective region. The Sun's radiative core and convective envelope represent the opposite configuration: radiative energy transport in the core, convection in the outer layers. This difference arises from the proton-proton chain's weaker temperature dependence and the increase in opacity in cooler outer layers. Different stellar masses show different internal structures. Stars below roughly 0.35 solar masses are fully convective. Stars between 0.35 and 1.3 solar masses have radiative cores and convective envelopes like the Sun, and stars above 1.3 solar masses have convective cores and radiative envelopes. Red dwarfs, stars with masses below roughly 0.5 solar masses, have core temperatures barely sufficient for hydrogen fusion. Their fully convective structure continuously mixes the entire star, bringing fresh hydrogen to the core and allowing complete fuel utilization. Combined with their extremely low luminosities, red dwarfs can burn hydrogen for trillions of years, far longer than the current age of the universe. The lowest mass stars formed shortly after the Big Bang are still on the main sequence today and will remain so for hundreds of billions of years. Massive stars, those exceeding roughly 8 solar masses, undergo far more complex evolution. After exhausting core hydrogen, they contract and heat sufficiently to fuse helium into carbon and oxygen through the triple alpha process. The carbon-oxygen core then contracts and heats, eventually reaching temperatures around 600 million Kelvin, where carbon fusion ignites. This produces neon, sodium, and magnesium. Further contraction leads to neon fusion around 1.2 billion Kelvin, oxygen fusion around 1.5 billion Kelvin, and finally, silicon fusion around 2.7 billion Kelvin. Silicon fusion produces ion group elements through a complex network of nuclear reactions. However, iron represents the end point of fusion energy production because iron 56 has the highest binding energy per nucleon. Fusing iron nuclei absorbs energy rather than releasing it. Fusion beyond iron is endothermic. The iron core grows until it reaches approximately 1.4 solar masses, at which point electron degeneracy pressure can no longer support it against gravity. Core collapse occurs catastrophically once iron core exceeds the Chandrasekhar limit. The core implodes in less than 1 second, reaching nuclear densities and rebounding to create a shock wave that propagates outward. This shock wave, energized by neutrino heating, disrupts the star in a core collapse supernova, the most energetic explosion in the universe aside from gamma-ray bursts. The core remnant becomes either a neutron star or, if massive enough, a black hole. Supernovae serve as cosmic forges, creating elements heavier than iron through neutron capture processes. The rapid neutron capture process, or R process, occurs in the intense neutron flux during core collapse, building elements up to uranium and beyond through successive neutron captures faster than beta decay can occur. The slow neutron capture process, or S process, occurs in the helium-burning shells of evolved stars, building elements through neutron captures with sufficient time for beta decay between captures. All heavy elements on Earth, the gold in jewelry, the uranium in nuclear reactors, the rare Earth elements in electronics, were created in stellar fusion and neutron capture processes, then scattered through space by supernovae and stellar winds. We are literally made of star stuff, as Carl Sagan famously noted. The calcium in our bones, iron in our blood, carbon in our cells, all forged in stellar cores over cosmic history. White dwarfs represent the endpoint for stars like the Sun that don't reach supernova conditions. After exhausting hydrogen and helium fusion, the Sun will shed its outer envelope as a planetary nebula, leaving behind a carbon-oxygen core roughly Earth-sized but with mass around 0.6 solar masses. This white dwarf will slowly cool over billions of years, radiating stored thermal energy but generating no new energy through fusion because temperatures never reach the roughly 600 million Kelvin needed for carbon fusion. Electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, supports white dwarfs against gravitational collapse. Electrons forced into tiny volumes resist further compression because quantum mechanics forbids multiple fermions occupying identical quantum states. This pressure doesn't depend on temperature, allowing white dwarfs to remain stable even as they cool. The Chandrasekhar limit of 1.4 solar masses represents the maximum mass supportable by electron degeneracy. More massive white dwarfs collapse further. Neutron stars, supported by neutron degeneracy pressure and nuclear forces at even higher densities, represent another stable endpoint for stellar remnants between roughly 1.4 and 2 to 3 solar masses. Above this limit, no known force can prevent collapse to a black hole, a region where space-time curvature becomes so extreme that nothing, not even light, can escape from within the event horizon. Binary stars with white dwarf components can undergo thermonuclear supernovae, type E Ia supernovae, through a different mechanism than core collapse. If the white dwarf accretes material from a companion star, pushing its mass toward the Chandrasekhar limit, compression reignites carbon fusion under degenerate conditions. The lack of temperature pressure feedback that normally regulates fusion creates a runaway. Fusion heats the star, increasing fusion rate, releasing more energy, in an explosive cycle that completely disrupts the white dwarf in seconds. Type Ia supernovae serve as cosmic standard candles in cosmology because they release relatively consistent peak luminosities, about 1043 ergs, allowing distance measurements to far galaxies. Observations of distant type Ia supernovae in the late 1990s revealed the universe's expansion is accelerating, leading to the discovery of dark energy, one of the most profound cosmological findings of the past century, recognized with the 2011 Nobel Prize in Physics. Stellar populations, groups of stars with similar ages and compositions, trace galactic chemical evolution. Population Y, stars like the Sun, formed recently from interstellar material enriched with heavy elements from previous stellar generations. Population 2, stars formed earlier from less enriched material and show lower metallicities. Population 3 stars, hypothesized but never definitively observed, would be the first stellar generation forming from pristine hydrogen and helium shortly after the Big Bang with no heavy elements. The Sun, as a population Y star with roughly solar metallicity and age around 4.6 billion years, represents a typical middle-aged star in the galactic disk. Understanding the Sun thus provides insights into billions of similar stars throughout the Milky Way and other galaxies. The detailed solar observations possible from our proximity serve as calibration for stellar astrophysics applied to more distant stars, observable only through their integrated light. Energy and technology. The nuclear fusion powering the Sun represents humanity's ultimate energy goal: clean, essentially limitless power from abundant fuels without greenhouse emissions, radioactive waste, or resource scarcity. Replicating stellar fusion on Earth has been pursued for over 7 decades, with substantial progress but persistent challenges remaining before practical fusion power becomes reality. Understanding solar fusion illuminates both why fusion energy is so desirable and why it's so difficult to achieve. The energy density of fusion vastly exceeds any chemical fuel. Deuterium-tritium fusion, the reaction most easily achieved in terrestrial fusion devices, releases 17.6 MeV per reaction, converting approximately 0.4% of fuel mass to energy. For comparison, burning hydrogen and oxygen converts roughly 10-38% of mass to energy. Fusion's energy density exceeds chemical combustion by 40 million times. Deuterium occurs naturally in water at roughly 1 atom per 6,500 hydrogen atoms, about 34 milligrams per liter of seawater. Earth's oceans contain roughly 1.4 x 10^21 liters, implying about 4.5 k 10^16 kilograms of deuterium. If fully utilized for fusion, this represents roughly 1030 joules of energy, enough to power human civilization at current rates for billions of years. Fusion fuel is essentially inexhaustible on human timescales. Tritium doesn't occur naturally in significant quantities because it's radioactive, with a 12.3-year half-life. Fusion reactors must breed tritium from lithium through neutron capture, 6 Li plus N, 4 Chi plus 3H. Lithium is relatively abundant in Earth's crust and seawater, though far rarer than deuterium. Combined deuterium-tritium-lithium fuel cycles could supply energy for thousands to millions of years, depending on reserves estimates and usage rates. The fundamental challenge in achieving fusion is creating conditions where nuclei overcome electromagnetic repulsion frequently enough to sustain energy production exceeding input. This requires temperature exceeding 100 million Kelvin, several times solar core temperature, to compensate for lower density achievable in terrestrial devices. At these temperatures, matter exists as fully ionized plasma, requiring sophisticated confinement systems. Magnetic confinement fusion devices like tokamaks use powerful magnetic fields to confine hot plasma in toroidal configurations. The tokamak design, developed in the Soviet Union during the 1950s, uses a combination of toroidal magnetic field from external coils and poloidal field from plasma current to create helical field lines that confine plasma away from material walls. The ITER project, an international collaboration under construction in France, aims to demonstrate sustained fusion power exceeding input power by a factor of 10. Inertial confinement fusion compresses fuel pellets using powerful laser or particle beams, achieving extreme densities and temperatures for brief moments sufficient for fusion. The National Ignition Facility at Lawrence Livermore National Laboratory achieved a major milestone in December 2022, producing fusion energy exceeding the laser energy delivered to the target, a condition called ignition. However, the laser energy represents only a few % of total electrical input, so net energy gain, including inefficiencies, hasn't been achieved. Achieving practical fusion power requires solving multiple interconnected challenges: heating plasma to 100+ million Kelvin, confining it stably for sufficient duration, achieving adequate density to drive fusion rates, extracting energy efficiently, breeding tritium fuel, managing neutron damage to reactor components, and doing all this in a system that produces more energy than it consumes while remaining economically competitive with alternatives. The Lawson criterion quantifies the conditions necessary for net fusion energy gain. Plasma must achieve a certain product of density, temperature, and confinement time for deuterium-tritium fusion, roughly 3x 10^21 keVs ets M3. This can be satisfied by high density and short time, inertial confinement, or lower density and longer time, magnetic confinement. The Sun operates at completely different parameters: lower temperature, but vastly higher density and timescales, achieving net energy through sheer volume and the availability of billions of years. Plasma instabilities represent major challenges for magnetic confinement. Disruptions, rapid loss of plasma confinement, can dump enormous energy into reactor walls in milliseconds, potentially damaging components. Edge-localized modes create periodic instabilities at the plasma boundary. Turbulence drives anomalous transport, reducing confinement efficiency. Controlling these instabilities requires sophisticated feedback systems, carefully shaped magnetic configurations, and active control techniques still being developed. Fusion's potential advantages over fission include inherent safety. Fusion reactions stop immediately if confinement fails, unlike fission chain reactions requiring active shutdown, and reduced radioactive waste. Fusion produces helium as the primary product, not radioactive fission fragments. However, neutron activation makes reactor components radioactive, requiring eventual disposal, though with generally shorter half-lives and lower radiotoxicity than fission waste. Even if fusion power proves technically feasible, economic competitiveness requires cost-effective reactor construction, operation, and fuel cycles. Current estimates suggest fusion electricity might cost comparable to fission or renewables in best-case scenarios, but substantial uncertainty remains until demonstration reactors operate for extended periods. The high capital costs of complex fusion facilities may favor large, centralized plants over distributed generation. The relationship between solar fusion and terrestrial fusion attempts highlights fundamental differences. The Sun achieves fusion through gravitational confinement. Its immense mass creates core pressures, sustaining fusion despite relatively low temperatures. Terrestrial fusion must compensate for lack of gravity by achieving much higher temperatures, requiring technological systems to confine and heat plasma to conditions exceeding the solar core. Fusion energy research has produced substantial scientific and technological benefits beyond direct progress toward power generation. Advanced materials, plasma diagnostics, superconducting magnets, high-power lasers, and computational techniques developed for fusion have applications in other fields. The international collaboration on projects like ITER advances scientific cooperation and technology sharing. The timeline for practical fusion power remains uncertain. ITER aims to demonstrate sustained fusion power in the 2030s. Demo reactors, demonstration power plants, might operate in the 2040s or 2050s. Commercial fusion power could arrive in the second half of the 21st century, though some private ventures claim faster timelines. Skeptics note that fusion power has been 30 years away for the past 70 years, though recent progress provides genuine cause for optimism. Regardless of when fusion power becomes practical, the pursuit advances fundamental physics, engineering, and materials science while working toward a technology that could transform energy production. The Sun has proven for billions of years that fusion can sustain enormous power output indefinitely. The challenge is replicating this process in systems compatible with human scales and timescales. Understanding that the Sun generates energy through nuclear fusion rather than combustion reveals profound truths about the universe's structure, evolution, and the origins of complexity. Fusion powers stellar evolution, creates the elements, drives galactic dynamics, and establishes the conditions necessary for life. The physics governing solar energy generation operates throughout the cosmos, shaping reality on every scale from stellar cores to galaxy clusters to the universe itself. The anthropic principle notes that we observe a universe compatible with our existence because our existence requires such conditions. Stellar fusion represents a necessary precondition for observers like humans. Fusion creates the elements composing our bodies and planets. The specific parameters governing fusion, nuclear force strength, electromagnetic force magnitude, mass differences between particles, must fall within narrow ranges permitting stable stars, long lifetimes, and heavy element production. If the strong nuclear force was slightly weaker, nuclei beyond hydrogen wouldn't be stable and fusion couldn't produce helium or heavier elements. If slightly stronger, fusion would proceed so efficiently that all hydrogen would have converted to heavier elements shortly after the Big Bang, leaving no fuel for stars. The electromagnetic force strength determines nuclear binding energies and Coulomb barriers, affecting fusion rates and stellar structures. The universe's compatibility with stellar fusion and chemical complexity appears finely tuned. Whether this fine-tuning indicates design, multiverse selection effects, or something else remains philosophically debated. From a physics standpoint, we observe that the fundamental constants permit fusion, and fusion created the elements necessary for complexity and life. The mechanism behind this apparent fine-tuning remains uncertain, but the fact itself profoundly shapes cosmic evolution. Stellar lifetimes set timescales for biological evolution. The Sun's 10 billion-year main sequence lifetime provided stable illumination for Earth's 4.6 billion-year history, allowing life to emerge, evolve complexity through extinction events and adaptive radiation, and eventually produce technological intelligence. Shorter-lived stars wouldn't provide stable conditions for billions of years. Much longer-lived stars like red dwarfs have extremely long lifetimes, but are cooler and have narrower habitable zones, potentially affecting habitability in complex ways. The habitable zone, the orbital distance range permitting liquid water on planetary surfaces, depends on stellar luminosity, which depends on mass through fusion physics. More luminous stars have wider habitable zones located farther out. Less luminous stars have narrower zones closer in. The Sun's luminosity places Earth comfortably in the habitable zone, though not centered. Venus is too hot and Mars too cold, suggesting the habitable zone's width is relatively narrow. Stellar evolution affects habitable zones over time. The Sun's luminosity has increased roughly 30% since formation due to helium accumulation, increasing mean molecular weight and core temperature. Earth's habitable conditions persisted despite this because greenhouse gas concentrations decreased over time, possibly through carbonate weathering feedbacks. In roughly 1 billion years, increasing solar luminosity will make Earth uninhabitable, even with minimal greenhouse gases. Runaway greenhouse effects will evaporate ocean. Eventually, when the Sun becomes a red giant in about 5 billion years, it will engulf the inner planets, definitely destroying Mercury and Venus and possibly Earth. The habitable zone will temporarily shift to the outer solar system. Jupiter's and Saturn's moons might experience brief periods with surface liquid water. After shedding the outer envelope and becoming a white dwarf, the Sun will slowly cool over billions of years, its habitable zone shrinking to distances closer than Mercury's current orbit. Galaxy-scale processes depend on stellar fusion. Stars convert gas into heavy elements, which enrich the interstellar medium through stellar winds and supernovae. Supernovae inject energy into the interstellar medium, driving turbulence and regulating star formation. Stellar radiation ionizes gas, creating HIE regions visible as emission nebulae. Black holes formed from massive stellar remnants can grow into supermassive black holes powering active galactic nuclei. The star formation rate in galaxies depends on gas availability, which depends on gas recycling through stellar evolution. Galaxies with high star formation rates rapidly deplete gas reservoirs unless replenished through gas infall or mergers. Elliptical galaxies have largely exhausted star formation, containing primarily old, metal-poor stars. Spiral galaxies like the Milky Way sustain ongoing star formation in disk regions where gas remains abundant. The cosmic star formation rate peaked roughly 10 billion years ago and has declined since as galaxies converted gas to stars and exhausted readily available fuel. The universe today forms stars at roughly 10% the peak rate. Over cosmic timescales, star formation will continue declining as gas reserves deplete, eventually producing a universe of aging stellar populations with few new stars forming. White dwarf cooling provides an independent age dating method for the oldest stellar populations. The coolest white dwarfs in globular clusters have had time to cool for roughly 12 and 13 billion years, providing a minimum age for the universe consistent with cosmological age estimates from cosmic microwave background observations and galaxy redshift measurements. This consistency demonstrates that fusion-based stellar evolution models correctly describe timescales. The ultimate fate of stars depends on mass, determined by fusion physics and degeneracy pressure limits. Low-mass stars become white dwarfs, supported by electron degeneracy up to 1.4 solar masses. Intermediate mass stars become neutron stars, supported by neutron degeneracy and nuclear forces up to roughly 2 to 3 solar masses. Higher masses collapse to black holes, where quantum mechanics' uncertainty principle and general relativity's gravitational physics create the ultimate enigma, regions where space-time curvature becomes so extreme that our current theories break down. In the far future, trillions of years hence, the last stars will exhaust their fuel and fade. White dwarfs will cool to black dwarfs, cold, dark stellar remnants emitting no light. Proton decay, if it occurs as some theories predict, will eventually disintegrate even these remnants over timescales of 1035 years or more. The universe's ultimate fate, whether expansion continues indefinitely, accelerates into a big rip, or reverses into a big crunch, depends on dark energy's nature, which remains poorly understood. Stellar fusion, by converting mass to energy via E-mc2, exemplifies the deep connection between matter and energy that Einstein revealed. The mass deficit in fusion, roughly 0.7% for hydrogen to helium conversion, becomes energy radiating through space, warming planets, driving atmospheric circulation, enabling photosynthesis. The Sun converts 4 million tons of mass to energy every second, yet this represents such a tiny fraction of solar mass that the Sun has consumed only 0.03% of its mass over 4.6 billion years. The universe operates through processes invisible in everyday experience. Quantum tunneling allows fusion despite classical barriers, mass converts to energy through nuclear binding, curved space-time creates gravity. These phenomena, revealed through patient observation and mathematical physics, demonstrate that reality operates on principles transcending human intuition. Understanding requires not just observation, but sophisticated theoretical frameworks validated through precise experimental tests. The sun doesn't burn, yet it shines. This apparent paradox resolves through physics operating at nuclear scales, where quantum mechanics and the strong force govern behavior. Fire represents electromagnetic interactions between electrons, while fusion represents nuclear force interactions between protons and neutrons. The million-fold energy density difference between these processes explains why combustion can power campfires for hours, while fusion powers stars for billions of years.